So this next lecture will be more conceptual and philosophical rather than being mathematically rigorous. So we'll start by discussing the Bayes theorem. The Bayes theorem is a simple idea which can be derived by manipulating the definition of conditional probability. So when we say A intersection B, this is basically same as saying B intersection A. So the probabilities of the two should be the same. We've seen previously that A intersection B appears when we tried defining the probability of A given B. That is, this conditional probability is the ratio of the probability of the intersection of the two sets divided by probability of the intersection of set B, or the event B, which basically allows us to write probability of A intersection B as the product of the conditional probability of A given B times the probability of B. So in a similar way, if you just interchange A and B, we can also write probability of B intersection A as the probability of B given A times the probability of A. So basically we can get this kind of an equality. This is precisely the statement of Bayes' theorem. Now, it seems like a simple relation, but it has far-reaching consequences when one starts looking into the interpretation of probability itself. So, that's what we'll look into in some detail now. So far, like I said in the beginning, we are dealing with the frequentist approach to probability. We started by laying down the three axioms. The probability of something happening out of all possible outcomes is 1. Probability of some event this lies between 0 and 1, where E is a subset of all possible outcomes. So this is one particular outcome out of all possible outcomes, a combination of those. And then if we had disjoint partitions of the set, then the probability of the union of those disjoint sets was just the sum of the individual probabilities. The formulation of probability that we develop starting from these three axioms is known as mathematical probability. And this was developed originally by Kolmogorov. And in this formulation, we can basically calculate the probability of any complicated event for which we know from before the probabilities of its components. So this is simple mathematics. Now, apart from this, So apart from this, next we have empirical or the frequency interpretation of probability. This is largely due to von Mises, and in this interpretation, probability is basically viewed as the limit of the frequency of a result of an experiment or observation when the number of identical experiments is very large. But the problem with this approach is twofold. So first of all, probability of xi defined like this is not just a property of the experiment. It depends on the ensemble or the collection of the n repetitions of the experiment. Secondly, there is a requirement that the experiment must be repeatable. Under identical conditions, along with a possibility for different outcomes. But this is a great restriction on the number of situations in which this concept of probability can be used. For example, if we talk about the probability of rain tomorrow, in such a question doesn't have any meaning for the frequentist school of thought, because the experiment cannot be repeated. And then we come to what is known as the subjective or the Bayesian school of probability. So this approach basically tries to extend the notion of probability to areas where the experiment of the frequentists cannot be repeated. So probability here is a subjective degree of belief which can be modified by observations. And this was the interpretation of mathematicians like Bayes and Laplace. So it takes Bayes' theorem as its starting point. So let's rewrite that. And then we interpret either A as theory or hypothesis, and B as the result or the observation. Then the probability of A, P of A, is the probability that A is true, or in other words, is represents our belief in the theory. So then Bayes' theorem can be rewritten as the probability of the truth of the theory given the result times the probability of the result equals the probability of obtaining the result given the theory is true times the probability of the theory being true. Or basically we can take this term onto the right hand side in the denominator. And we can get this equality. So now if you look carefully, you can see that this equation makes sense. So if the theory predicts the result with high probability, that is, if P of result given theory is true is large, then of course the probability of theory being true based on the result is also large. There is a direct proportionality between this conditional probability and this conditional probability. Now let's say we want to determine some parameter of nature. So I want to determine lambda through an experiment which has an outcome. It will denote by capital Z. Now we know the conditional probability density function of seeing this outcome Z given lambda as f of Z given lambda. Now before doing the experiment, our prior belief about lambda is given as P prior of lambda. Now the probability of Z which will denote by P of Z is basically, especially if you are dealing with the total probability, is equal to the marginal probability density function f1 of z, which is given by the sum over all these lambda primes, and we are taking the product of the conditional probability of z given this possible priors times the probability of the prior. And then Bayes' theorem allows us to compute the posterior probability. Or if even lambda is a continuous variable, instead of having the prior and posterior probabilities, we'll have the prior and posterior probability density functions. And now the marginal PDF, instead of being given by the sum, is actually given by an integration. Now, if the prior probability is given, then this whole formulation is fine. But the problem is this here exactly. How do we quantify this prior probability to begin with? Now, guessing the prior probability is subjective and unscientific. The usual prescription for remedying this is the following, which is known as Bayes' postulate. That if we are completely ignorant about P prior, then we take all values of lambda as equiprobable. Of course, there are objections to this postulate. So, for example, if we are completely ignorant about p lambda, how do we know that the prior probability is a constant? Secondly, even a slightly different choice of the prior probability will give an entirely different posterior probability. The third objection is an extension of the first one. If we are ignorant about the probability for lambda, we are also ignorant about the probability for any function of lambda. Such as p of lambda square or p of root lambda or p of 1 by lambda, etc. But if we take any one of these as constant, then that would imply a different prior probability for lambda, and finally giving a different posterior probability. Now the objections are usually answered by this assertion, which is supported by experience, the posterior probability usually converges to the same value, so near about the same value after several experiments. Irrespective of the choice of the prior. Now this brings us to an important question, that in real world application, do we favor the frequentist approach or the Bayesian approach. So it must be noted that the sense in which probability is used in topics like quantum mechanics, or statistical mechanics, is in fact in the sense of frequencies. Now, as far as experimental results are concerned, in physical sciences, most experiments are repeatable and we can say that the problem specifies a collective or an ensemble. So we see that the frequentist approach is all around us, and the frequentist interpretation makes sense in such scenarios, especially given the objections in the Bayesian approach. A large proportion of physicists today would claim to be frequentists. But when we start interpreting experimental results, and the manner in which this is done is more akin to the Bayesian school of thought. So as an example, let's say the mass of the electron was measured in some experiment to be a value like this, 520 plus minus 10 kilo electron volt per c square. What this basically means that we measured 520 keV by c square with an apparatus that has a resolution of 10 keV per c square. Now, the language normally used to report such findings is the mass of the electron is close to 520 keV by c square. Or we may say mass of the electron is between this interval of 510 to 530 keV by c square with 68% probability. But note that this is not the frequentist probability, because the experiment has not been repeated an infinite or even a large number of times. So this sounds more like a Bayesian probability. So let's say with a error or a resolution is comparable to, let's say, the standard deviation. of 10 keV by c square, the probability of measuring a mass m when the true value is me, let's say this is proportional to exponential of minus the square of m minus me by 2 sigma square. Then using Bayes' theorem, the probability that the true mass has the value me after we have measured a value m can be given by Bayes' theorem. So we see that this is proportional to this conditional probability of observing a mass m if the true mass was me. And let's say we have assumed the prior to be constant. So this will come out to be proportional to that same expression. In a frequentist interpretation of probability, the electron has a definite mass, and the probability that it has that mass is 1, and the probability that it has some other mass is 0. So in the frequentist interpretation, the statement that the electron has a certain mass with a certain probability does not make any sense. Now, when we say that the probability that the electron has a fixed mass in the frequentist interpretation, the problem is that we do not know what that value is. So, we make statements like these. The mass of the electron is between 510 to 530 keV by c square. And we make this claim with 68% confidence, let's say. Now, this term is important and disappears when we start introducing statistical concepts like maximum likelihood estimation, confidence intervals, and so on. So, the Bayesian school of thought will play a prominent role when we start looking into statistical inferences of these experiments, or the results of these experiments.